Scientists at the Max Planck Institute for the Science of Light have managed for the first time to create a unidirectional device that significantly increases the quality of a special class of transmitted signals in optical communications, optical vortices. By transmitting selective optical vortex modes exclusively unidirectionally, the developed device largely reduces detrimental backscattering to a minimum. The scientists emphasize the great practical utility of their discovery in many optical systems, with applications ranging from mode division multiplexed communications, optical tweezers, vortex lasers to quantum manipulation systems. Optical communication can be improved by increasing the amount of optical information transmitted. This can be achieved by using multiplexed channels such as using many optical wavelengths, different polarization states or multiple time slots. In the last decade, optical spatial modes, which are the eigenfields in the waveguides, are widely exploited to further improve the communication capacity due to the little crosstalk between orthogonal spatial modes. In classical communication as well as in quantum communication, the use of vortex modes in multiplexing methods has proven to be advantageous. This special mode set possesses a helical optical phase distribution and allows an additional degree of freedom for multiplexing optical signals. Devices like vortex generators, lasers and signal amplifiers were demonstrated and are in great demand. A limiting effect on the applicability is that there has not yet been a device that permits transmission of certain vortex modes in one direction but not the opposite one. However, just this kind of device, a so-called optical vortex isolator, is of crucial importance for the improvement of signal quality and purity. The particular difficulty in developing such a device is a fundamental principle of optics: reciprocity. It requires a symmetrical response of a transmission channel when the source and observation points are interchanged. Researchers succeed in building an optical vortex insulator now. A team at the Max Planck Institute for the Science of Light led by Xinglin Zheng, Philip Russell and Birgit Stiller, achieved a breakthrough that makes this possible. They used sound waves that propagate only in one direction to break T. The effect of so-called topology selective Brillouin-Mandelstam scattering in chiral photonic crystal fiber allows for a unidirectional interaction of vortex carrying light waves with traveling sound waves. A specific optical vortex can be strongly suppressed or amplified with a well-designed control light. The experimental results published in Science Advances show a significant vortex isolation rate, preventing random backscattering and signal degradation in the system. This is the first non-reciprocal system for vortex modes, which opens up a new perspective in non-reciprocal optics. The same physical effect can happen not only on the fundamental modes but also on higher-order modes, says Xinglin Zheng, the first author of this paper. The light-driven optical vortex isolator will have great impact on the applications such as optical communications, quantum information processing, optical tweezers, and fiber lasers. I find the possibility of selective manipulation of vortex modes solely by light and sound waves a very fascinating concept, says Birgit Stiller, the leader of the Quantum Optoacoustics Research Group. Make a difference. Sponsored opportunity story source. Materials provided by Max Planck Gesellschaft. Note: content may be edited for style and length. Journal reference: Xinglin Zheng, Philip Street J. Russell, Christian Wolff, Michael H. Frosch, Gordon K. L. Wong, Birgit Stiller. Non-reciprocal vortex isolator via topology selective stimulated Brillouin scattering. Science Advances, 2022. 842, doi. 10. 1126, Sci-Adv. ABQ6064. Cite this page, Max Planck Gesellschaft. Breakthrough in optical information transmission. Sound waves that propagate only in one direction break the light transmission reciprocity. Science Daily. Science Daily, the 31st of October 2022. ift.tt/fk0 Beige. Max Planck Gesellschaft. 2022, October 31st. Breakthrough in optical information transmission. Sound waves that propagate only in one direction break the light transmission reciprocity. Science Daily. Retrieved October 31, 2022 from ift.tt/fk0 Beige. Max Planck Gesellschaft. Breakthrough in optical information transmission. Sound waves that propagate only in one direction break the light transmission reciprocity. Science Daily. https://ift.tt/fqi0byg. Accessed October 31, 2022. Thanks for watching. Please subscribe my channel for more videos.